My project looked at the thermodynamic factors involved in the dissolution of a salt. I had learning objective 6.24, which is the student can analyze the entropic and enthalpic changes associated with the dissolution of a salt using particulate level interactions and representations. Before we move into our learning objective, there are a few terms and definitions that we need to go over. Let's first review what enthalpy is. Enthalpy is a thermodynamic change that measures a system's internal energy plus the product of its pressure and volume. In simpler terms, it is energy absorbed or released from a system. In a system with constant volume and pressure, the energy absorbed or released is equal to the change in enthalpy. Entropy is a thermodynamic function that describes the randomness and disorder of molecules based on the number of different arrangements available to them in a given system. To show our learning objective, let's make a quick model. With just a little bit of flour, some salt, some water, food coloring, and oil, we've made the base to our model. Now simply rinse and repeat for different food colorings, and voila, wow. Let's see the final result. Here we see the application of Science Practice 1, where we exhibit our understanding of the learning objective by using Play-Doh models. In our model, we will be looking at the dissolution of the salt copper sulfate in water, where the pink Play-Doh balls represent the copper, and the orange connected to the blue represent the sulfate, and the toothpicks represent the bonds. Let's first look at how the entropy of the system is affected when the copper sulfate is dissolved in water. As water is slowly added, the copper sulfate splits into its complementary ions, copper 2+, and sulfate. The orientation of the water molecules is due to the partial charges of the H2 atom created by its polarity. Here we see Science Practice 7, where we are able to connect the dissolution of a salt to periodic and intermolecular trends. There is a partially negative side on the oxygen, which attaches to the copper 2+, and there's a partially positive side of the hydrogen, which is attracted to the sulfate ion. As you can see, the copper sulfate split into two particles, doubling the amount of particles in the reactants. With more entropy, there is increased disorder and an increased amount of arrangements that the particles can be in. Now let's look at how enthalpy is affected when copper sulfate is dissolved in water. As water is added, energy is absorbed from the surroundings in order to break the bonds between copper and sulfate. The copper sulfate separates into copper 2+ and sulfate, and once again forms intermolecular bonds with H2O due to water's polarity. This process releases energy into the surroundings, since forming bonds releases energy. It is important to note that the energy required to break the initial reactant bonds is far greater than the energy released when forming these weak covalent bonds between the ions in water. By evaluating the dissolution of copper sulfate, we showed Science Practice 5.1 as we analyzed the intermolecular and thermodynamic patterns and interactions of the dissolution of a salt. Now let's see the enthalpic changes of a dissolution of a salt in real life. The initial temperature of this warm water in this cup is 101.3 degrees Fahrenheit. However, after mixing in salt, the temperature changes to become 99.6 degrees Fahrenheit. This shows a positive enthalpy change with energy being taken in from the surroundings to break the initial bonds, resulting in a lower temperature. Overall, the dissolution of a salt resulted in both a positive entropy with more disorder and a positive enthalpy with more energy being used from the surroundings to break the reactants bonds than energy released from new bonds forming.